Hey, hope you're doing well today. It's good to talk to y'all again here. Um, Going to do a new lesson today. It's section 11.3, more on limits. So, hopefully you remember what a limit is. Because this lesson's all about them, basically. So this is like the grand finale lesson here on limits. Alright, so here is the informal definition of a limit. Basically, you have some function f of x. X is approaching a, and a is a member of the real numbers. So basically, a is some number, okay? And L is some number. We can write this, okay? So as x goes to some number, okay, on a function, then the y value goes to L, okay? So it's arbitrarily close to L because sometimes there are numbers we can't actually get to, like infinity, or places where there's a vertical asymptote. And the reason why this is an informal definition is because close to, okay, that's kind of a informal way of defining it. Are we close to Johnstown? Are we close to Pittsburgh? Are we close to New York City? Okay, so it's kind of a vague definition. What does close to actually mean? All right, there's a more formal definition of it. It involves epsilons and deltas, and we're not going to bother with it. All right, so you might do it next year in calculus. All right, so limits have these properties here. Okay, these are basic rules of limits. You can go ahead and look at them for a little bit here. But basically, it kind of allows you to, if you have like two functions and you're adding them, you could split it up and do the limit of each separately. Same goes with subtraction, multiplication. You could multiply the two functions, or you could take the limit of that function and multiply it by the limit of the other function. If there's a constant that's multiplying the function, you could pull that constant out of the limit, okay, and you'd get the same answer if you have the constant times the limit. You could split a limit of a fraction where there's a top and a bottom. You could split it up into two different limits. It doesn't matter if you take the power first or you do the limit first, okay? And then the root rule is kind of like the power rule. You could do the root first, or you could do the limit first, then take the root of it. All right, and it has to be a square root or higher. It could be a cubed root, etc. All right. You've seen this before, one-sided and two-sided limits. Okay, so you want to look and see that little, is there a minus or is there a plus here? Okay, so and when you have left-handed limits, you'll have a minus. So x is getting close to some number from the left side of a graph. Okay, and when there's a plus, it's coming from the right side of the graph. Okay, so it's coming from the opposite direction. So, and these actually are not true limits. Okay, these are like parts of a limit. Okay, you have the left approaching and the right approaching. Okay, and so this definition here, this theorem of one-sided and two-sided limits, says that a function has a limit if and only if the left and right-handed limits are equal. So in other words, a limit exists, okay, only if you get to the same number from the left side and the right side. And if you get to a different number from the left side and the right side, then there is no limit for that particular number. And I'll show you an example of this later here in a minute. All right. And then definitions as it goes to infinity. We can't actually get to infinity. Yeah, so I'll just let you guys look at that and read it, but you guys have seen limits as they go to infinity. So x approaches positive infinity, it's going to the right. X approaches negative infinity, it's going forever to the left. All right, so here's a couple examples of solving limits by direct substitution. So when you're solving a limit by direct substitution, well, you're simply substituting, okay? And there isn't going to be like a whole vertical asymptote if you can solve a limit by direct substitution. So let's show you what this would look like then. All right, so the limit as x approaches 0 of this function is, well, you just substitute 0, okay, in place of each of the x's. So you have e to the power of 0 multiplied by sine of 0. Okay, so what is e to the power 0? E to the 0 power. Okay, e to the 0 power is 1. Okay, anything to the power 0 is 1, by the way. All right, now what is sine of 0? So think about your unit circle. I know it's been a while with that, but start here, okay? So sine of 0, this represents the angle, okay? So the angle is 0, so you're right here at the x-axis here. All right, and so what is sine of 0? Well, this coordinate here is 1, 0. Now, if you remember, okay, the x value goes with cosine. Okay, so cosine is the x value, and sine is the y value. So, all sine of 0 is equal to is 0. Okay, so sine of 0 is equal to 0, and if we do this problem, then we just take 1 times 0, and so the limit evaluated as x approaches 0 of this function here is equal to 0. All right, these problems are right from the book. There are some more good examples in the book in section 11.3. So I encourage you guys to find your book and check out those examples if you need some help. I'm just doing the actual homework problems from the book because, well, it's the easiest thing to do, and you can look at the other examples and maybe those will help you out a little more. But these two are pretty simple. Direct substitution is pretty straightforward. You just have to be able to figure out what's going on here. All right, so natural log, we got a ln here. Ooh, fancy ln there. All right, sine, so you got the sine function. You're substituting pi in place of x, pi over 2. All right, so let's think back to good old unit circle here. Where's pi over 2 at? Okay, hopefully remember pi over 2 is 90 degrees, okay? Pi is 180 degrees, 3 pi over 2 is down here. So you have pi over 2. Well, what is the sine value of pi over 2? Well, if sine is y, okay, the y value at pi over 2 is 1. So sine of pi over 2 is equal to 1. So you have natural log of 1. All right, and then you could use your calculator and type in natural log of 1. But in essence, this is saying, okay, what you want to think about here is e to what power is equal to 1. Because remember, natural log, the base on natural log is e, okay? And so if you're doing natural log of 1, you're taking the base and you're trying to figure out what power. Okay, so for like log and natural log, you're actually trying to figure out the exponent. Okay, so e to what power x is equal to 1. And like I said in this last problem, e to the 0 power is 1. So natural log of 1 is equal to 0. All right, so those were a couple of the harder substitution ones. The other ones, you just kind of just plug it in and get an answer out, and they're a little bit easier there if you look at the book's problem in section 11.3. All right, let's go to another one here. Let's see where we're at. Yep. All right, we're going to go to this one and clear this ink out of here so you can see it a little better. All right, why cannot you use it by direct substitution? All right, so if you look at this one, if you try to direct substitute on this guy right here, you're going to get a divide by 0 error, okay? So you're going to get the bottom over 0. And that's why you cannot substitute directly to get an answer here. So what you have to do is try to cancel out the denominator to get an answer. All right, so before we go ahead and we substitute, you have to factor it, okay, and try to cancel out whatever factor on the bottom will give you division of 0. Okay, so this numerator factors into, let's see, factors of 12 that give you 7. All right, that's 4 and 3. Okay, so we have x plus 4, x plus 3. All right, now in the denominator, x squared minus 9 is going to give you x plus 3 and x minus 3. Cool beans there. Alright, so guess what? These x plus 3's, they cancel out like so. And now, see, if you substitute the negative 3 in, it will no longer give you division of 0 because that factor has gone away. So let's go ahead and let's substitute. We'd have negative 3 plus 4 on the top, and negative 3 minus 3 on the bottom. So the limit here would be negative 3 plus 4 is 1. Negative 3 minus 3 is not 0. That's negative 6. So your limit for number 11 is negative 1, 6. Okay, so the limit of this function is negative 1, 6. Alright, you do the same thing on number 12. It's just kind of like reverse, so I'm not going to bother doing that one for you guys. You just got to factor the bottom, factor the top, and it will cancel out here. One of the factors, probably the x minus 3 factor, will cancel out. Alright, number 17 is a little bit different. Okay, so if we directly substitute, you're going to get the square root of negative 3, which is an imaginary number. And you can't have an imaginary limit, okay? So that doesn't make sense there. All right, and so when a factor doesn't cancel, okay, so like let me graph what this looks like real quick. So remember the square root function looks what it looks like. Okay, it's shifted right 3 because of this minus 3. So you're like right here at 3. The square root function is going to kind of go like that. All right, so as x approaches 0, there is nothing on the graph. All right, so the limit as x approaches 0 is none here. And you can have a limit that simply doesn't exist, or there is no limit at that particular point. Okay, if the graph doesn't cover it, the limit isn't there. All right, so let's move on here to another scenario. All right, so here you have the graph and you're figuring out the limits, the left tail, right tail, and combination of the limits looking at them. So let's check these out. All right, so the limit as x approaches 3 from the left side. So we're looking at this right here, okay? So we're going to 3 from the left side. And what is the y value as we're going to 3 from the left side? It's simply 2. Okay, so that's nice. All right, what about as we go from the right side? Okay, so we're going, following the graph this way. You see, what's the y value here? Oh, it's equal to 4, okay? So you actually go to like where the graph goes. You have to follow the graph. I know it does this jump here, but you're following the graph. So like where was the graph at when it got really close to 3? It was up at 4 if you're going from the right side, but it was down at 2 if you're going from the left side. So what is the limit if you combine both of them? Because they're not agreeing, okay? Since they're not agreeing and they're different, that means we don't actually have a limit here. Okay, so there is none for C. Okay, so it doesn't exist. There is no limit there. All right, compare that to question 29 here. Okay, as we approach 3 from the left, so let me switch to a different color here. So we're approaching 3 from the left, we get the number 4. Okay, as we approach 3 from the right, hey look, we get the number 4 too. So the combination of both of them, they're agreeing here, the limit as x approaches 3 altogether is equal to 4. All right, so hopefully that's enough to help you with the homework there. I'll go ahead and post that for this section of problems. Don't forget I gave you a bunch of review problems already too, so you might want to go and do those today some more if you haven't done a lot of them yet. But you're going to have another section to do on just this section 11.3. All right, so if you guys need help, please email me. I'd love to help you guys, and I hope you have a great day. Praying for you all, and just hang in there. We're almost done. Got another month to go here. Take care now. Bye-bye.